Hello everybody, good morning or possibly good afternoon. For me it's afternoon, in fact we're approaching 4 o'clock here. I'm here today to work through another topic of the second half of AP Calculus BC. In this video I'm going to work through the topic of Power Series Convergence, and although that name is a good description for everything we're going to be focusing on, talking about how a power series converges or diverges and the properties therein, I think the best way to describe this would be to describe the two topics that we're going to address as they'd be described elsewhere, which is the radius and interval of convergence. So we're going to talk about these two properties that a power series has, or possibly doesn't have depending on how that power series is constructed. We'll discuss what it means to have a radius or interval of convergence. We'll talk about the different types of intervals of convergence. There are 3 that are out there, and the radii that go along with them. And I'll try to demonstrate a couple different examples for you, as well as give you some visual intuition or graphical intuition at the very beginning. It'll in fact be where I begin. Before things kick off, just a couple things to talk about. Well, as I try to avoid the news a little bit more lately, basically just everything's kind of on pause. I think it's been officially said that all the shelter-in-place things will go through the end of April at the earliest. That'd be the earliest possible things. So small little things that have happened, like I got the notice from Broadway Sacramento about season tickets, so I donated the cost of those tickets back to them because I know they're going to be hurting with an entire show canceled, and truthfully I realized probably the second show that scheduled for May, which interestingly enough is about the aftermath of 9/11, that will likely have to be rescheduled or postponed or canceled, so I'll donate that back to them too if it comes to that. So little things like that have been popping up. In addition, had my first time, I got to see a friend yesterday. A friend of mine was riding his bike around and just texted me to see if he could come over, and I said no, just because I know you're not supposed to. So instead he stood with his bike on the sidewalk, and I talked to him from my doorway, so that way it was we were totally safe, because his dad and my dad both have suffered from respiratory conditions in the last year. But it was nice just for 45 minutes to talk about stuff, talk about math for him, talk about grad school and the PhD program he's going into, and just, I guess we were talking about the world and talking about Zoom all the time. Everyone's into Zoom right now. But just kind of get some stuff off your mind, because it's one of the things that, it's great to talk on the phone. I get to talk on the phone with a couple people each week, and obviously text messaging is nice, but don't get to see anybody at all. So it was really nice. It was a really appreciated thing. I appreciated having that, hour to talk to him or so. Hope you are all well where you are, and hopefully you're finding ways to keep busy and comfortable and stay connected to people. Sometimes connection is an easy thing to take for granted and to forget about, but oftentimes, especially with the technology we have, it's just one reach out away from the opportunity to remind yourself of how important those other people are, and how easy it is to connect in some way. No, it's not the same. I'd much rather be able to give people a hug and, see people face to face. But, if 15 feet between me and the sidewalk is the best way I can do it for now, that's what I'm going to settle for at this point. So, having said that, I do want to jump into the lesson here and kind of talk about this topic. So we'll go ahead and kick that off right about now, before I wander into the world of COVID-19 and the pandemic. So the topic of power series convergence. To begin with, before I talk about or kind of show you some things that will help you visualize what it is that we're going to be looking at today, I want to start with this statement that I wrote out. And I considered not writing it out, and then when I read it, I was just like, no, this does a really good job of kind of kicking things off. So first and foremost, what this says is it says that a power series is a function of x, and it has the form given right down there. And we talked about that before in the previous lecture, the idea that there's a certain structure here that resembles what looks almost like a Maclaurin or Taylor kind of polynomial too. But it's the function, It's the function of x of that form with its domain given by the set of all x values for which the series converges. Now, this is not something that we've thought about up to this point. We've just kind of treated power series as functions of x, and we said that's kind of all there is to it. But the truth is, we can actually talk about whether or not that function, that power series, has a given value in its domain by checking to see if the series we get when we plug in that x value is going to converge or diverge. So it's a little bit to say right there. So let me demo this first, and then we'll do the visual stuff. So the first thing I want to do is I want to write out a given power series. And of course it's going to be a power series, so it will fit that form that we were just looking at. We'll do this one. Let's make sure I choose the one I have over here. We'll choose x minus 4 to the n power. So that's our series. So now in this case, what I want to do is I want to demonstrate that this power series, which clearly is a power series based on the structure that it has, I mean, look how much it looks like this, meets our definition for sure. But I want to point out that for some values, this power series converges, and for other values of x, of course, it will diverge. So let's plug in a value here. Which one did I use in my example? There we go. Let's plug in x equals 6. Let's start there. So let's see. If we plug in x equals 6, what's that going to do? Well, that's going to give us a new version of the series. It'll give us the series from 0 to infinity of 6 minus 4 to the n power. And in fact, we could go a step further than that. We could do the sum from 0 to n of 2 to the n power. Now this series is the series that multiplies every term, every previous term by 2. So we're just multiplying by 2 over and over again, which means it's geometric. And in fact, this is a geometric series. So this is geometric series. And specifically, it's a geometric series with that ratio, that common ratio, equal to 2 being greater than 1. What that means is that this series diverges. So what we've just seen is that if we plug in, let's make sure I spelled that correctly, yes. If we plug in x equals 6 to this particular power series, it turns out that the series diverges. That means that 6 is not in the domain. So it's a nice little thing for us to come to the conclusion of. So we've just shown that there are, in fact, some values that simply don't make this series, or that don't fit into the domain. On the other hand, we could pick a different one. We could put, let's see here, let's put 4.5 in. I think that's probably what I put in. Yeah, it is. So if we put 4.5 in, then in this case, our series will be the sum from 0 to infinity of 4.5 minus 4 to the n. And clearly, when you subtract 4.5 minus 4, you're going to get 1/2 to the n. In this case, we also have a geometric series, where you notice we're just multiplying over and over again by 1/2, and that geometric series has an r value of 1/2, and that is clearly less than 1. What that means is that the series converges. So in other words, if we plug x equals 4.5 in, unlike what happens when we plug in 6, if we plug in 4.5, we get a convergent series. That means that 4.5 is in the domain. So in other words, we found one value that happens to fall in the domain. Now, having said all that, obviously this was just a very simple example that I came up with and cooked up here just to kind of demonstrate this idea of the domain of a power series. The truth is, our job today, our purpose, is going to be figuring out a method and determining and practicing a method that will allow us to determine what the domain is of that power series. And in other words, what we're really asking is, what are all the x values for which this power series will converge? Because of course there's different x values we could put out there, and in some cases it'll be any x value. In other cases it's going to be every x value or just a small finite interval of a certain finite width. So our job is going to be trying to answer that question. When does this power series converge? And we're going to translate into the question what x values are, or what are the x values for which this power series converges. Now, having said that, I've talked about the idea of there being something called a radius and an interval of convergence, two different topics. And the truth is, even though plugging in values certainly gives you a demonstration that some things are in the domain and some things aren't, I would love to actually show you what this looks like. Because so far you've had a kind of different perspective on how power series and Maclaurin and Taylor polynomials actually work. So let's start here. I don't know if you'll recall this, but back when we first began this unit, I started by talking about a couple functions that had very neat and powerful looking Taylor polynomials. So here's one. Specifically, this is a Maclaurin one, excuse me. What I want to point out here is this is e to the x being stitched together. It's obviously not quite as satisfying as e to the x, but notice that as it keeps adding terms right up here, it just keeps giving us more and more of the e to the x function. It's almost like the further we go, the more it's stitching to this curve. Like we're just getting a better picture of this function for a wider interval. In fact, let me emphasize that idea of an interval here. So I don't know that you're going to be able to see this. Yeah, okay, so it's that blue line right down here. You can see it highlighted right there for the moment. I'm going to actually subtract it down a little bit just so you can see the interval. So this is a representation of where this, on what interval this thing seems to be converging. So there it is. The blue thing's telling you the x values for which this series seems to be converging. Now at this point you can see it seems to be keeping up pretty well, and obviously it's stretching a little bit on the right side too, because of course even though this curve is growing really fast, it is getting closer and closer there as well. But notice that what's really happening is this interval just keeps getting wider and wider. In fact, if I centered this thing better, we'd see that it's actually like going pretty well and seems to be centered around that 0 value that we know is the center of this thing. In fact, there we go. I stopped there at 74 terms, but basically you can see that we've got a lot of this curve represented right now. Like, we've done a pretty nice job. The truth is, though, that type of behavior, the behavior where the series just keeps getting bigger and bigger and bigger and bigger, or converges more and more and more and more and more, is only one possible type of convergence we might see for a given power series, aka Maclaurin polynomial. Let me instead offer you this situation. So we haven't analyzed this type of function before. We haven't analyzed this one just yet, although we'll get to see it, I believe, in the next lecture. But for the moment, this, well, right now this is a line. But if we extend it out a little bit more, you'll see that this actually is the power series for this rational function. Now, the fact that this is rational probably already gives you a little bit of pause, because, of course, there's a vertical asymptote there. And how's a polynomial going to handle that vertical asymptote? Well, more than that, I want you to look at the way this thing converges. Now, keep in mind, with e to the x, as we added more and more terms, we just got a greater and greater section of the curve converge to. Watch what happens with this one, though. So again, it's definitely converging. You can watch it converge here. But do you notice that, like right here, this blue thing just kind of, it's not running in that direction anymore. It's just kind of stopping. It just seems like it's kind of reached its limit. It's almost like there's an asymptote on how far it's converging. And in this case, it's going pretty well. I mean, it's slowing down and grinding to a halt, really. But it seems to be going okay. Now let me add something else here. Let me add the interval of convergence as well. And just like I did before, let me go ahead and drop it down a little bit so we can see it a little bit better. So here's a visual representation of the interval on which this thing is converging. Remember the last one just kind of like and just kept getting further and further out? This one seems to be kind of stopping. It's still growing a little bit. It's like watching snails race. It's just kind of there, but it doesn't look like it's going to get all the way over there or all the way over there. It just kind of looks like it's stopping somewhere around, it looks like 5. Maybe a little wider than that. It's just, we're not quite getting the picture that we want. So unfortunately, what this is showing us is that some power series just don't have a wide interval on which they converge. There's only a few finite small width or narrow interval of x values on which this thing will actually converge to the curve. This is a function where it only can converge so much. There's just nothing happening past that point. It just doesn't model the function behavior anymore. And what that means for us is that means that we're getting situations like this first one where it's just given all those other x values are ones that make the series diverge. So it doesn't actually converge to the function any more than it would anything else. So there's a real nice tie between this domain idea and the convergence or divergence of a series and what we saw in that visual picture. What we're trying to determine in this lecture is, of course, what we saw if we went pretty far out. We're trying to figure out, of course, what is this interval on which the x values seem to converge? And then after that, like, how would we describe the size of it with something called a radius of convergence? So that's where we're going. That's where we're starting out with. Just want to give you a little bit of visual intuition, as I like to do. From here, let's go investigate these properties that these series are going to have. So on this next page, what I have is basically the breakdown. This is the graphic organizer. I already did the graphic and the organizing for you. This is how power series can possibly converge. There's not some fourth one out there that you're just not ready for. No, this is it. This is how they converge. There are 3 ways that we have possible. And what you saw on that last page was you saw 2 of these possibilities. What you missed was the first one up there. But beside the point, let's talk about these possibilities. First, on the left column, I have a description of the convergence. So for instance, the first one says a way that the power series could converge is it could converge only at its center x equals c. And now this is probably the most boring and least interesting version or type of convergence that's out there. But basically there could be some series that are so divergent in behavior, they grow so fast, that the only point at which they're actually going to converge is going to be at the center itself. Now, if you think about it, the reason why at the center itself it might converge and nowhere else is because if you plug in C to a power series, you get a sub n times the quantity c minus c to the n, which means the series is really just 0. And 0 converges really nicely. It's 0. It's as convergent as they can go because there's nothing literally there. So that first possibility is if it converges only at its center, then what happens is, because there's so few values that on which it can converge, it means the interval of convergence that we see right over here is literally just the center itself. So however you want to describe that, it's only at that one single x value where the series will converge. And then more importantly, because there's only one x value, there's no width to the interval because there's no interval. So the radius would have, or it would have a radius of convergence of r equals 0. So that radius of convergence is a measurement of how wide the interval of convergence will be. So basically kind of a proxy for how much convergence is out there. How many x values will there be that we can find this series converging for? So there's that first option. The second option, written in the middle, number 2 in light blue, says that it's possible that the series could converge for all real numbers. Now we saw an example of this first one. We saw just a few moments ago the fact that one example here, one example would be the function y equals e to the x. We saw that as we added more terms, we just got a larger and larger set of x values on which the curve was matching e to the x. That's a good sign that we have an interval of convergence that is all real numbers. And in fact, e to the x, sine of x, and cosine of x are the 3 functions for which this happens supernaturally. I believe there are others out there, and of course there are modifications of these 3 functions, but the biggest thing to note is that those 3 do have a special property that they converge to the entire function if we keep going further and further out and add more and more terms. So as it says in this case, because it's all the numbers, basically every number is possible, we need to describe that as a really wide interval because it doesn't really matter what x value we plug in, it's still going to converge. The way to describe that width is of course to say that the radius is infinite, meaning that if you start at the center, whether it's 0 or c or something else, we're going to go infinity to the right and infinity to the left because that way we cover the entire interval of real numbers. So in fact, there we go. R is equal to infinity. Also, though, I will point out, not that interesting. Just like, oh, all the numbers work, thanks. It's like, I can't think of a good example. I was going to say, it's like if someone gives you a gift and you're like, oh, cool, thanks for giving me that gift. I feel so special. And then you find out that person gave a gift to every one of the other 2,900 students in the school. Like, obviously, it's still a nice gesture. Don't put that away. It's still cool, but it's not quite as interesting as, like, getting a special gift yourself. The last one, if you're looking for interesting, the last one is the only one that's truly interesting, and it's the one we probably spend the most time working with. In option 3, it says, the series could converge on a finite interval centered at x equals c. So in this case, the reason this is interesting is, of course, there are lots of centers and there are lots of distances and widths in which it could converge, because now we're just talking about a finite interval. So this is what we noticed on that one function. Let's go back there for a second. If you recall, we noticed this with this rational function, that this was a situation where there was just a finite interval on which the series converged to the function. So that was an example of that particular one that we noticed. Now with this one, this last one, this is the one that requires the most calculation, although all 3 of these will begin in the same place. But it's just worth pointing out that the other thing that's kind of difficult about number 3, in exchange for all that interestingness and like, oh cool, it's doing something, the challenge is then you have to check the endpoints. The endpoints really, really matter here because it's possible that although you might find the interval of convergence really fast and know what x values work, those endpoints can behave somewhat differently. And truthfully, if you're asking me for my money, checking the endpoints is by far the most challenging portion because it requires you to pull in all of those series test, what's the word I want? All those series tests basically at a whim, like going, oh, there's the structure of a limit comparison, so I'm going to say that one diverges. Like that kind of stuff is all going to pop in. So having said that, we're probably going to spend most of our time on number 3, although at the same time I'm going to demonstrate one example of each type of convergence for you in just a second. Before we go forward, actually, let me add one more little thing here. I notice it's not in here. Truth is, I'd love to remind you that this is describing the x values. Like, in a sense, this is the domain of the power series. These are the x values for which the series converges. So I should have had x's there, and I probably should have had an x right there. I did better on the red one at the beginning. Okay, having said all that, the last thing I want to point out is that our path to figuring this out is not going to be figuring out what my system was on Desmos and doing it that way. Our system is actually going to be something very straightforward. It's literally one of the convergence tests. We'll begin every single problem in which we seek a radius or interval of convergence by jumping in and using a particular test. That test is the ratio test. I don't think I did a good job of building up the excitement about it. But the how of interval and radius of convergence is we're going to use the ratio test. I don't have a great set of explanations to show you exactly why, but the ratio test does a nice job of giving us a structure that kind of resembles geometric series, where there's already kind of a finite interval, right? Because geometric series, r has to be between -1 and 1, so there is something kind of natural about using the ratio test. So that's really going to be it. We're going to use the ratio test. We'll go through, do some work. I'll show you the structure to get there. And then after that, we will, of course, wrap things up by checking the endpoints and then stating our interval. So having said that, like again, graphic organizer, really nice to have. I definitely recommend that if you're someone writing down these notes, which many of you probably are, this is probably the biggest thing to include in there, in addition to any examples we work through. So of course, if you think I'm going too fast, if you think I'm going too fast, slow it down or pause it. If you think I'm going too slow, there's a speed up button. So be you, and we'll be good to go. Okay, let's take a look at that first example. And notice in this first example that we are asked or tasked with finding both the radius and interval of convergence for this power series. And I will say that power series looks pretty intimidating. Now, having said that, these things, once you get more comfortable with them, there's something that you could probably anticipate almost in your mind the more comfortable you get and the more intuition you have about series. But for now, as always, when I work through these problems, especially for the first time with you, my goal is to be as careful and thorough and precise as I possibly can, trying to show as much stuff. I'll be reasonable, of course, but I'm going to work much more carefully than I would if I was doing this myself, trying to demonstrate everything for you, particularly in a situation like this where I don't have the ability to answer your questions as they pop up. I'd just rather be thorough, so I apologize if that bothers you that I'm working super carefully, but again, this is the best I can do under these circumstances. So as I mentioned on the previous page, if we wanted to determine the radius or interval of convergence, and they're both kind of on the same path, what we need to use is the ratio test. And in fact, step one is literally that. We're going to use the ratio test, or sometimes I'll refer to it as the ratio test. So for the ratio test, the way that's going to work is, of course, if you'll recall, we'll take the limit as n goes to infinity of the absolute value of the ratio, a sub n plus 1 over a sub n. So now in this case, when we go to evaluate this ratio, I want to balance two needs. Of course, I want to be as accurate as possible, but I don't want to take up a ton of space just because there's a limited amount of space here. And of course, I want to move through at a pace that's reasonable. So having said that, I'm going to do a couple things. So first and foremost, when I go to set this up, I'm going to let the absolute values nerf what we call the toggle. That -1 thing, the absolute value is going to make it so everything's positive. So the -1 thing is not going to be relevant for us at this time. So I'm going to let that thing go. But I will point out, the absolute values don't disappear with the toggle because of the fact that the x values in here could in fact make this inside or this base equal to a negative number. So in fact, we'll end up with the negative or the absolute value still included in there. I'll show you what it looks like. I just want to kind of get that out of the way. Second, when I go to write this thing, I don't want to have to do a huge stack, like ratio over another ratio, what's called a complex fraction, because that would just be very space and time intensive. So instead, I'm just going to take advantage of the fact that really we're dividing one ratio by another one. So that's a fraction divided by a fraction. So I'm going to flip or take the reciprocal of the second one and then multiply them. So having described all that algebraic stuff first, my first move here is, of course, to rewrite the limit. Inside my ratio, I'm going to have the absolute value still. As we said, the toggle was nerfed, so it's no longer in there. We'll have x plus 2 to the n plus 1 divided by, and it looks like in the denominator we'll have n plus 1 times 4 to the n plus 1 And then we'll have, on the other side, we'll flip the ratio. And this will be the one that's inside the sum and already. So here we are. Okay, having written that out, give you a second just to look at that. I next want to prepare it to decompose and to break it down and clean it up a little bit. So again, keeping the absolute values there. We'll have x plus 2 to the n times x plus 2 all over, let's see, we'll have, actually let's start moving these things together. So I'll put this over x plus 2 to the n. Then in addition, we'll have times n over n plus 1. And then for the 4's, we'll have 4 to the n divided by 4 to the n times 4 to the 1. And there is our ratio, kind of organized a little bit. Now I'm going to break my color system here a little bit. The 4 to the n's divide out, and the x plus 2 to the n's divide out. So where that leaves us is with a much cleaner version of this ratio. We will have the limit as n goes to infinity of now inside, we've got the absolute value of, it looks like, x plus 2 divided by 4 times n over n plus 1. Now having said that, I'm going to rewrite this a little bit too. Now since n's going to infinity, specifically positive infinity, the n and n plus 1 are definitely positive. And in fact, I could go ahead and rewrite this a little differently for another reason too. If this limit has only n values in question, this thing is technically an constant almost. It's like it's irrelevant. It's not being affected by the n's. So there's a couple different moves I can make here. The simplest one I'm going to do though is I'm going to rewrite this as the absolute value of x plus 2 divided by 4, and then times the limit as n goes to infinity of n over n plus 1. Now we've done this limit before. This limit's going to be equal to infinity over infinity, or it's going to go towards infinity in the numerator and infinity in the denominator, which means that then of course we could use L'Hopital's rule and we could get 1 over 1 is 1. So in other words, this ratio is going to be equal to the absolute value of x plus 2 divided by 4. And of course I can move the absolute values off the 4 because 4 is already positive. Am I sure? Yes, I'm positive. It always goes like 20% longer than I think it will. Okay, so regardless, we now have evaluated the limit of the ratio. The problem is the ratio test isn't complete until we compare this to 1. And since we want the ratio to we want the series to converge, since that's really what we're talking about. It's the radius and interval of convergence, not divergence. That means we need this ratio to be less than 1. So in other words, what we've just established is an absolute value inequality, and it's our job to solve it. So at this point, if we were going to go to solve it, we could do that and jump right in. But let me point something out first. Let's point one thing out. Specifically, let me point this out. After you've done the ratio test, you can actually get the radius of convergence really, really quickly. When you reach a point where you can say the absolute value of x minus c is less than r, then that tells you that r is equal to the radius of convergence. So for us, as soon as we can reach that point, we can automatically answer one of these two questions. We can find specifically the radius of convergence. And so that's where we want to start our attack here, because we've almost got that ready to go right over here. So having said that, let's finish this off. If I multiply both sides by 4, we'll be able to get this expression right here turned into the absolute value of x plus 2 is less than 4. So what that tells me right away is that my radius of convergence is going to be equal to 4. And that's a huge victory. We already have one piece of the information that we were asked for. We wanted two things. We've got the first one already there. So that's a good sign. We know the radius of convergence here is 4. This definitely is one that has a finite interval, so we're describing a situation 3 in the green down there. That's a good thing. But of course that's not enough. We found the radius of convergence. We want to find the interval of convergence now. So let's see. Once we've got that, our next move is going to be to actually solve for that. So at this point, the best way to describe this is we're going to solve for x. So what I mean is we want to take this expression we now have that gave us the radius and we want to actually solve it. So over off on the side, I've now got this inequality. Absolute value of x plus 2 is less than 4. So I want to solve this. Now specifically this is a conjunction, so I'm going to try to save a little bit of time and space See if I did anything fancy. No, I just did it right. So let me point out that in conjunction form, this is the same thing as saying that x plus 2 is going to be between -4 and +4. And once we've done that, we can solve this inequality by subtracting 2 from each side. As soon as we do, we end up with this. -6 less than x less than 2. Now this is what I call the raw interval of convergence. And the reason I call it the raw interval of convergence is because it's not quite finished. We aren't finished cooking this interval of convergence because we need to consider the endpoints. I'd probably try to make some sort of analogy to cooking a steak or something, but truthfully I'm not very good at that, so I'm not gonna make any sort of insinuations about my ability to cook anything that doesn't require a microwave. So instead, let me just point that out. This is the raw interval of convergence because we're not done. What we have to do is we now have to check the endpoints. So this final step, which I'm going to make in a bright red color, is literally that. We need to ensure that the endpoints are verified because it's possible that both of them could provide a convergent series. It's also possible that neither one could, or just one or the other could. So basically we want to now plug in those two endpoints, which for us are going to be -6 and 2, into our original series and see what the result looks like, so we can check to see if it converges or diverges. So let's see what happens. And you can see how this can be a little space intensive already. Well, it's going to get worse. So here's what we got. If we plug in x equals -6, we'll start there first. If we plug in -6, our series will go from n equals 1 to infinity of, it looks like, -1 to the n plus 1. And then on the inside here, we have -6 plus 2 to the n, all over n times 4 to the n. So now at this point, I want to clean this up a little bit. So let's do exactly that. Our series from 1 to infinity is going to be -1 to the n plus 1. Then we'll have -4 to the n. And then we'll divide this thing by n times 4 to the n. So having done all that, now we can clean it up even a little bit further. So we'll go from 1 to infinity. In this case, this is kind of a weird one, but we're going to have -1 to the n plus 1. We have -4 to the n over 4 to the n. That's going to simplify to -1 to the n. And then all in the denominator, the only thing we'll have left then is just n. And now, since we have -1 to the n plus 1 and -1 to the n, we combine that into n equals 1 to infinity of -1 to the 2n plus 1 divided by n. Now, it would seem like this is suggesting that we have some sort of alternating series, but be careful. In that power, 2n plus 1 is always going to be odd, which might be an odd fact, but so things go. Since that's always odd, that means that this series is effectively n equals 1 to infinity of -1 over n. This is just the harmonic series times -1. It's literally just what I'd call the negative harmonic series. So in fact, what we can say is that this is going to be a divergent series. And I would say, like, it's a little bit harder to say why, but I would say by properties, let's see, how did I say this before? Oh, I guess I did it even safer. I was going to say when I did this earlier, I put by the -1 times the harmonic series. So in truth, this isn't the best explanation in the world. It feels less formal than it could have been, but it's actually authentic. Like, that's really why. It's just a constant or a scalar times the harmonic series, which we know diverges. So what that tells us is that x equals -6 is not in the domain of this power series, which means this is not going to be included in our interval of convergence. So what we've just confirmed here is that indeed this is going to be a less than. We've just confirmed it. Now, having done that, let's next look at the other endpoint. So we did x equals -6. Let's do x equals 2. So if we plug in 2 here, and geez, you can tell this is kind of annoying to put in down here. We'll have -1 to the n plus 1. This will be times 2 plus 2 to the n. All of this is going to be over n times 4 to the n. Oh, this one looks like it's going to be a friendlier one. From 1 to infinity, this is -1 to the n plus 1. Over here we'll have 4 to the n We'll have it over n times 4 to the n, and wouldn't you know it, 4 to the n's divide out. That leaves us with this, the sum from 1 to infinity of negative 1 to the n plus 1 divided by n. Now, don't be too hasty and say, oh, it diverges harmonic series. Keep in mind that in this case, we have our toggle actually changing the sign up top, which means this is an alternating series. And if we check the two properties, which I'm going to do just by inspection or verbally right now, the first property is, do the terms get smaller in magnitude? And the answer is yes. As n gets bigger, 1 over n keeps getting smaller. We know that. And second is the limit as n goes to infinity of the magnitude of the term 0. And clearly that's true as well. So this one actually converges. And it converges specifically by alternating series test. In fact, this is probably a poster child example of the alternating series test. Like, it's a great one. It's actually not an absolutely convergent series. It's conditionally convergent, but for us, that's good enough. It's on the flipping and the toggling side here, so we're good to go. So that means that instead of having less than 2, we're going to have less than or equal to 2. And what that leaves us with as our final conclusion is our interval of convergence. I was going to put IOC, but the International Olympic Committee's got enough on their mind right now with having to postpone the games. So instead, that tells us our interval of convergence is either going to be -6 less than x less than or equal to 2, or if you prefer interval notation, you could say x is a member of -6 to 2 with a hard bracket on there. So it's totally up to you which way you decide to go, but that is our process. And truthfully, remember at the very beginning I said that of this problem, I said checking the endpoints is pretty much as the hardest part. It takes forever, it's the longest part, it's the most nitty-gritty. Honestly, it took about the same amount of space as doing that massive ratio test did. But the important thing is, of course, that we can dig through this, and the ratio test provides our guide to work through the rest of this problem. So there is all of our work. We found it out. It tells us what our interval of convergence happens to be. If you wanted to check your answer because you just don't trust me or something, even though I'm wearing a tie and everything, you could go on Wolfram Alpha, do a good job. You could also try to figure out what function this represents, and then you could try to see if it converges on that interval, but that's going to be a pretty challenging version. So instead, there is that full technique, and now that we've done it once, let's do it with a couple other examples. Maybe some quicker ones, though, just to be safe. Okay, next one we're going to hit is same approach, same question. In fact, I literally just copied the question. It took forever making sure it looked really nice when I wrote it. We want to find the interval of convergence for now, this series right up here, which has n factorial times x to the n plus 1 over 2 to the n. So for the moment, I will point out that as you look at this for the first time, nothing probably jumps out at you. There is something that's like glaring that you'll notice by the time you've done this problem set or kind of thought about it for a while that would lead you to a conclusion about the type of convergence here. But for now, let's play along just like we aren't sure what's going on. So to begin with, as we mentioned, oops, that's purple. I wanted to stay faithful to my original colors. To kick things off, we want to take the limit as n goes to infinity of the ratio, the absolute value of the ratio of a sub n plus 1 over a sub n. So we start there. Just like before, well, there's no toggle here, so we don't actually have to worry too much, but we'll get this thing started. We'll have the limit as n goes to infinity of, we'll have n plus 1 factorial times x to the n plus 2, all divided by 2 to the n plus 1. And then we'll multiply by the reciprocal, so 2 to the n, all over n factorial times x to the n plus 1. So from here, as we did before in the previous problem, I want to go through and try to break this thing down so I can see all the parts. So we'll set that up. We'll have n plus 1 factorial, which is the same thing as n plus 1 times n factorial. And of course that will be over n factorial. So we'll start there. Oh, I really wanted to straighten that line. It's bugging me. I can still do it. I can hear your judgment through the computer and through the future times. Yep. So after we've done that, next we have x to the n plus 2, which is the same thing as x to the n plus 1 times x. So once again, we'll see some stuff going away pretty cleanly. Then last but not least, we have 2 to the n in the numerator and 2 to the n times 2 in the denominator. Just as we did before, we'll divide out some of these pieces. So the n factorials go, the x to the n plus 1s go, and the 2 to the n's go. What that leaves us with, after all that little bit of work, we get the limit as n goes to infinity. So cleaning things up a little bit, I see in the numerator, we'll keep the absolute value there. We have n plus 1 times x divided by 2. And just as we did in the previous one, anything that doesn't have an n in it can be pulled out in front as a scalar, even though obviously x is changing, just not a function of n. So we can rewrite this as the absolute value of x over 2 times the limit as n goes to infinity of, and on our inside, we just have n plus 1 left. Now, if we take the limit as n goes to infinity here, we're going to get the absolute value of x over 2 times infinity plus 1. That is equal to infinity. So, interestingly enough, our ratio is going to infinity. The question of when is this less than 1, that's really our question here. In fact, we should probably change colors here. Our question of when is this less than 1, well, the truth is infinity is not less than 1. That's they're very different numbers. $1 or infinity dollars. Your life outlook looks very different. This is one of those situations where you look and go, well, that's not true. And in fact, that's probably how I'd respond to this. Never. Never is infinity less than 1. What that tells us is we've just shown that this thing just doesn't converge. And in fact, that means the only place this could converge is at its center. So based on this piece, since it never converges, well, since we get that never statement, what that tells us is that it only converges at x equals its center. Looking up here, there's nothing with that x. It's not x minus c at all, which means it only converges at x equals 0. In fact, I should write in the word converges. So it converges at x equals 0, and specifically converges at x equals 0 only. And what that means for us is that our radius is equal to 0, because there's only one x value for which it converges. And our interval of convergence, notice we don't even have to continue here. No endpoints to check this time. Our interval of convergence is going to be simply 0. That's it. There's only one value that makes this series converge. And we checked it. And that was it. And we're good. That's all. There it is. That's all she wrote. So now, in fact, we have our answer. Of course, this is kind of tricky. We got infinity out of the ratio test. You might think, oh, radius equals infinity. But no, remember, it's very important to compare that to 1. That's really what the ratio test does. But do let me point one thing out here before we move forward. I mentioned at the very beginning of this problem that there's something about the structure of the summand, there's something about the structure of this power series that suggests to me that it's going to behave a certain way. What I noticed here, just so you were all on the same page, I noticed the presence of a factorial in the numerator. The reason I bring that up is as that factorial is in there, factorial grows really, really fast. It's one of the fastest growing functions. It's no Ackermann function, but it's out there. The reason I bring up n factorial is if it's in the numerator, that means the term's magnitudes are going to grow bigger and bigger and bigger. They're just going to keep growing really, really fast because as you plug in larger n values, that factorial is going to be much, much, much larger over time. And if we keep adding larger terms, it means it's going to diverge. It's just not going to have a chance to converge. So in fact, as soon as I saw that, I knew for certain, that this thing was going to only converge at its center. So although it was obviously beneficial for us to see it happen, it's very important to note that sometimes as you get more and more comfortable with these things, sometimes you'll notice the presence of something, and typically it will be a factorial, that will give you a hint as to the type of convergence that a function has, or a power series has. So there was our second example. You've now seen 2 of the 3 situations that were described in our graphic organizer. But you know what the heck, third example, maybe this third example won't be the third one, because, there's no way, why would I do that? Yeah, of course it's going to be. But let's play along and pretend like it's not there. Okay, we have a third example. I just want to keep getting a few options out there for you. This totally we don't know or anticipate what's going to happen based on the structure of lessons in the past. So let's work through and take a look at this new series. So we want to now check for the radius and interval of convergence for the series given by x to the n over 2n plus 1 factorial. As with every one of these problems, we begin with the ratio test. So we want to figure out what the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is, and then of course we want to compare it to 1. To start with though, we'll start with the limit of that ratio. So in our particular situation here, let's see what I can do here. I'm going to put the absolute values in. Of course there's an x in there. There's no toggle for us to nerf or deal with, but we still need it in there. This will be x to the n plus 1 divided by 2 times quantity n plus 1, all plus 1 factorial. And then we'll multiply times the reciprocal, since that's what dividing by fractions really is. It'll be over, oops, terrible division sign. Oh man, embarrassment. There it is. And it'll all be over x to the n. Simplifying and cleaning this puppy up just a little bit, we're going to now have, let's see, absolute value of x to the n times x divided by x to the n. On the numerator, we do have 2n plus 1 factorial, but that denominator's factorial, there's a lot going on in that thing. So let's take a look at that one. That 2n plus 2 plus 1, that's the same thing as 2n plus 3 factorial. But for the sake of space, 2n plus 3 factorial is something we can calculate. It's 2n plus 3 times 2n plus 2 times 2n plus 1. And at that point, you probably noticed what I did, which is, hey, our factorials match. It's a factorial. So having said that, we now have our expression ready to go. Just as we've done in the past, we can simplify. So the x to the n's divide out and make a 1. The 2n plus 1 factorial goes away. And that leaves us with a, stellar ratio for us to analyze. We now have the limit as n goes to infinity of, let's see, we've got the absolute value of x divided by 2n plus 3 times 2n plus 2. So now at this point, if we follow the same pattern as before, we would pull that absolute value of x out in front, treat it as a scalar when we're evaluating a limit in terms of n, and that's totally fine for us to do. But you may already be catching on to something kind of troubling here. If we do that, or whether we do it or not, it should be a 2, whether we do it or not, what happens is we get the absolute value of x, that thing that's very crucial for us, but it's being multiplied times this limit of something that has a finite numerator over a function of n. That's going to give us the absolute value of x times the value of this limit, and 1 over infinity times infinity is equal to 0. So in this case, no matter what x value we plug in, it doesn't matter which one we choose, we get 0. Now having said that, getting 0, again, your mind might jump to like, oh, the radius is 0. But no, that's not true. Because now that we found that, that means that no matter what x value we plug in, our ratio is 0. And that means that 0 is less than 1, and that is always true. Meaning it doesn't matter what x value you put in, it's always going to converge. This converges at all the x values. And what we're saying all this time is if it converges always, let's make sure I write this out here. If the series converges always, what that tells us is that converging always means that our domain is all x values. Doesn't matter which one we put in, this is going to be a convergent series. And so having said that, that's exactly what we end up with. We end up with a series converging for all x values. And so as far as our answers go, our radius is equal to infinity because it's converging for all the x values, probably even write that in there, all x. And then in addition, our interval of convergence is going to have to reflect that it's all x values, and in our case that's going to be equal to negative infinity to infinity, or all real numbers. Your call, your preference. There it is. And so once again, just like with the previous example, this is one of those special cases, and this is one of those situations where you might notice the presence of something that kind of guides you towards this conclusion right off the bat. Having a factorial in the denominator means that our denominator is growing super fast. Growing super fast. So it's growing super fast squared. I don't know what I meant by that. The denominator is growing very, very rapidly. Its magnitude is getting huge really fast. What that means is it doesn't matter what numerator we have, because there's that factorial down there, means the denominator is going to dwarf any growth of the numerator, which means this is going to go towards 0 really fast, and it's going to converge really readily. In fact, so readily that it doesn't matter what x value you plug in. You want 42? Go for it. I could put in 42,042,042 in for x, and it would still converge. So just another one of those nice things, like noticing the presence of a factorial oftentimes gives you some clues right off the bat that this is going to be one of the two specialer cases, as opposed to the wide interval one we saw earlier. Having said that though, that does in fact get us through that third example. Obviously not as rich. I mean, look at how much work we did on the first one versus these last two. I guess it's probably a relief when you get one of these because it means you get to do a little bit less. But at the same time, just find it far less interesting than that situation 3 with the finite interval. Having said that, I think we're at a really good point for you to take a moment to just kind of practice this. Obviously, in a classroom setting, I wouldn't have the ability to stop here and just let you work through a whole series of problems on your own at your own pace like I can here. So I guess yay, silver linings for this whole thing. Basically, I'd encourage you to work through these problems. The first one asks you to answer some questions about domain. The second one is a traditional kind of interval of convergence question. And the third one asks you just about the radius of convergence. There's a special thing that I want you, a piece of information or a result I want you to kind of pull out there. So as with all the previous ones, I'm going to encourage you to work through these triads. When you finish, check your answers, in this case on a Google form. I set this up. I think this is a really natural one for you to put things through. There are some restrictions when you try to put in your answer for 2b, which is about the interval of convergence, but they're all described on there. So please do take a look when you get there. But I think this will really help cement the skill and give you a chance to grapple with it. If you're looking at how difficult are these problems compared to things, the first problem isn't a full radius and interval of convergence question, but I think it's a good one for you to look at. It does a really nice job of having you think about endpoints and convergence and stuff in ways that maybe you haven't recently, depending on how much time has been spent between going through the previous unit and this one. The second one is very much a middle-of-the-road traditional kind of problem. I'd say that it's a easier problem from the mid-level or mid-tier radius and interval of convergence problem. Not a lot of tricks and twists, but definitely a great one to look at. And then the last question has kind of the only algebraic challenge that's out there. So I think it's a good one for you to see, but I wouldn't ask you anything beyond what you're being asked right down there either. So having said that, please do take a look at these triads, work through them. In just a bit, when you finish, obviously come right back, and then I'll wrap up the lesson just by talking about some of the intuitions you might develop as you look at these power series, so that maybe you can anticipate what the answer is going to be and slide through some steps a little bit, in fact. So please do that, and then come right back here. Okay, hopefully that's given you enough time to work through those triads and you used the solutions that I'm sure are in the drive or are going to be there soon or posted somewhere else possibly. Having said that, the last thing I want to do is just get you an opportunity to think about how you can look at the structure of a series and anticipate more or less what's going to actually happen with it. So I have in front of me 5 problems. We're obviously not going to do these 5 problems, and this is indeed the last part of the lecture. This is just something that I think is beneficial because it reminds you that there are some structural indications here to lead us towards some of these conclusions. And hopefully this will be a beneficial, just quick little interjection. If not, focus on the assignment and just focus on kind of working through the techniques and getting comfortable with them. So as we look at these expressions, the first thing I want to point out is that 2 of these problems instantly scream what's happening with those series. And the problems that in particular scream to me what's happening are in particular A and C. So what I want to point out here is that the presence of a factorial expression, an n factorial expression, immediately tells us that we aren't going to have one of those finite intervals. We're going to end up with one or the other here. So specifically on the first one, because the factorial is in the denominator, that means that our ratio is going to approach 0. And because of that, that means our ratio will be less than 1 always. What that tells me is that our radius is going to be infinity, and our interval of convergence is going to be all real numbers. So again, that n plus 2 in the denominator, you can use it as a tool to make you think of cosine and sine and e to the x, all of which have that n factorial in the denominator. Those guys converge for all values. This is going to converge for all values as well. On the other hand, in part C, we have that n factorial in the numerator. So while the first one, the n factorial in the denominator, kind of led us along this path, The second one has n factorial in it, or sorry, c has n factorial in the numerator. What that means is that the ratio is going to approach infinity. And since infinity is never less than 1, that's going to give us a result of the ratio being equal to 0 and our interval of convergence simply being a single value. And I'll put c in there, but the truth is for this one, our center value would just be at 0. So if you want to be more specific for this one, it would be at 0. So the first way you can kind of anticipate what's happening, particularly if you're short on time on one of these problems or you're just trying to kind of get through the idea really fast, is look for the presence of an n factorial expression. If it's in the numerator, that's going to cause the terms to flood and grow super fast, which is going to mean the series will diverge all values or converge at just the center. On the other hand, if the factorial is in the denominator, excuse me, if the factorial is in the denominator, that's going to cause the opposite to happen. It's going to cause the ratio to go to 0, which will mean it converges everywhere. And it'll behave like e sine or cosine does. Now from there, that leaves us with the other possibilities. So to look at those and kind of anticipate what's happening, I find it helpful to start by looking at the center first. So with each of these, let's start by trying to identify what the center is. So looking at the first one, to find my center, I look at the x to the power part. So because this has x plus 1, that leads me to believe that our center is -1. On the ones down below, looking at the x part here, I see x by itself. That tells me that my center is going to be simply x equals 0. And then for the last one, I'm going to be a cheap person, and I'm just going to point out that also, once again, we have just x by itself. That leads us to see that the center is going to be 0. So that's us looking right there, or right there. Now, in order to draw conclusions about the specific radius, the way we look is we look at the coefficients that are around. So on this top one, I notice that I have 3 there. That 3 in the denominator, if we imagine, we're going to eventually get something like absolute value of x plus 1 over 3 is less than 1. And that leads me to believe that our radius here is going to be equal to 3. Likewise, on the next one that I see, there's no number down here being raised to the n power. We just have a factor that has an n in it. And those factors, as we've seen before, if we go through the ratio, it'll be something like the cube root of n plus 1 over the cube root of n. So those things all go to 1. So what that leads me to believe is that our denominator basically just has like a 1 to the n, which leads me to believe that r is equal to 1. The last one that we have here, it's very tempting for people to simply immediately go, oh cool, that means the ratio is going to, or the radius is going to be 11. The problem is here, the difference between E and B and D, and this is a really small thing, but hopefully something you saw in the try it. So if you did try it part number 3, you've already kind of seen a preview here. The problem is our expression with x has 2n in the power. What that means is that really we're going to end up with x squared being less than whatever the radius thing would appear to be. And in this case, following the pattern that we did before, we'll end up with the absolute value of x squared, or just x squared, being less than 11. What that means is our radius is going to be not just 11, but the square root of 11. So I'd say this is probably the toughest problem on here. This is the one that involves the most extra stuff, but at the same time we can still get to the radius pretty quickly from there. Last but not least, as we go to look at this, once we have a center and a radius, we can conclude what our interval of convergence is going to be. So for this first one, since our center is -1 and our radius is 3, we'll have -4 up to 2, because that way we're doing -4 minus 3 and -1, oh, excuse me. Excuse me. So I said -4 minus 3. I meant -1 minus 3 and -1 plus 3 as our values. Down below, looking at the other ones, if we look at our interval of convergence for E, well, following 0 and plus or minus root 11, we'll have -root 11 to positive root 11. And then for the last one we have over on the left, our interval of convergence would include -1 and 1. Now you'll notice here that I did not mention at all what the endpoints are. If we wanted to check the endpoints, we'd absolutely be able to. It just kind of takes a little bit more effort to get there. In this first one that I see up here, as I plug in those values, basically I'd have one option to look at. I could look at both of these things. In fact, I believe that this one in particular is going to go to have both of those endpoints diverging. I could be completely wrong. Let me see if I actually have that in there. Now I'm pretty sure I'm correct though. The reason is if we plug in -4 or 2 up in here, that's going to give us either plus or minus 3 to the n over something involving something involving 3 to the n, and we'll be left with just -1 to the n times 1. So this will either be plus or minus 1 we're going through. Pretty sure that will be our interval of convergence. The bottom one, down at the bottom, if we look at the endpoints, if we plug in -1, we'll have an alternating series, which means it's going to converge by the alternating series test. So we'll actually include -1, whereas if we plug in 1, we'll have 1 over the cube root of n, which is a divergent p-series. So I would anticipate the interval of convergence to include -1, but not +1. And then for the last one, this one's a little bit tougher for us to get through, but in this case, it's going to behave almost identical to the one we saw up above in part B. We'll have something where it's -1 to the n times either 1 or -1 to the n, which will diverge in both cases, which I noticed I didn't even do on the earlier run-through of the notes. So there it is. Having said all that, obviously my goal isn't for you to do these problems in your head. I mean, just take a look at that work. This is not in-your-head work. Like, I want you to be much more careful than that. What I wanted to point out to you, though, is at the very least, you can probably cut down your job if you can anticipate the interval of convergence really, really fast, or at least the raw interval of convergence, so that you can focus your attention on checking the endpoints, which tends to be the more difficult and the more time-consuming part of this calculation. In addition, you can completely exclude all of that work if you just recognize the presence of where those factorials are and what that implies about the type of convergence you're going to run into. So having said that, again, this last little bit was just kind of an extra opportunity for you to kind of see how you can get really comfortable with things or look at different behaviors and anticipate maybe what the answer is going to be. Obviously, I don't endorse that as a good strategy when you're first kicking things off and digging into interval and radius of convergence today for the first time. But at the same time, as you get deeper into the unit, it might be worth your time to do exactly that and to save yourself a little bit of computation, calculation, and actual work and dig through to get to your answer. With that said, that basically concludes our lesson. As I said, there's not a lot after that point. It's just an opportunity for you to practice. So I would encourage you to, if you haven't already, to definitely work through those triads. I think they do a really good job of cementing the skills. And of course, take a look at the problem set as a tool to help you practice and really cement the skill in a different way, like basically preparing and seeing what it's like to do it yourself and checking answers as you go along the way. So as always, thank you for watching. I hope that this video has been a helpful tool to teach you this other concept, a concept that shows up pretty frequently. I'm not sure, I don't believe it's included on the AP exam in 2020, but in any other year not featuring a massive global pandemic, absolutely it will be. So definitely worth looking if you're watching this from the future. But no matter what, again, I enjoy being able to make these videos and deliver you the curriculum as best I can, under the circumstances, which are far from ideal. I even dressed up for you a little bit today, trying to, add a little bit of class to the presentation once more. Should have used my British accent and added even more class to the proceedings. But, oh, we're here already. So I miss you guys. Thanks for watching. Hopefully this is a good tool for your learning. And no matter what, stay safe, stay well, and looking forward to seeing you again. Not through imagination in this webcam thing. So have a great night. Goodbye.